Your server handles 100 requests a second. Traffic is at 80 per second, so you're at 80% capacity, and the average wait is 50 milliseconds. Traffic grows 10% to 88. You still got headroom. What happens to the wait? Intuition says it goes up a bit, maybe to 60. It goes to about 104. You added 10% load and doubled the latency, and you weren't even close to full. Queues are one of the few places where the maths is genuinely counterintuitive and also directly useful. Today, how random arrivals actually behave, why variability alone creates queues even when you have spare capacity, the nonlinear blow-up as you approach full utilization, and why adding a second server helps far more than doubling the speed of the first. Here's the mistake. If 100 customers arrive per hour, it's tempting to reason as though one arrives every 36 seconds. Neat and evenly spaced. Under that assumption, if you can serve someone in 30 seconds, no queue ever forms. Every customer is finished before the next appears. On paper, at 80% utilization, you'd never wait at all. But arrivals aren't evenly spaced, they're random. And random means clumpy. Sometimes 3 people arrive in the same 10 seconds, and then nobody comes for 2 minutes. The average is unchanged, but the clumps create a queue, and here's the asymmetry that drives everything. When you're idle, you cannot bank that spare capacity for later. Idle time is gone forever, but a backlog persists and accumulates. Queues remember the bad periods and forget the good ones. The standard model for this is the Poisson process, and it says something quite specific. Events happen at a constant average rate, and each event is independent of the others. From those two assumptions alone, the number of arrivals in a fixed window follows the Poisson distribution, and the gaps between consecutive arrivals follow the exponential distribution. Both are one line in number py. Poisson with a lambda for counts, exponential with a scale for the gaps. And the exponential one has a genuinely strange property worth pausing on. It's memoryless. If you've already waited 5 minutes for a bus, the expected further wait is exactly the same as it was when you arrived. The process does not owe you anything for having waited. Let's simulate arrivals over an hour and look at the gaps. The histogram is piled up hard at 0 and tails off to the right. Most gaps are short, a few are very long. That shape is exactly what clumping looks like as a distribution, and it's the opposite of the evenly spaced picture we assumed a minute ago. Now the queue itself. This is queue length over time in a simulation at 80% utilization. It's not stable at some comfortable level. It spikes, drains, spikes again. Now here's the same system at 95%. Same arrival process, same service time, only slightly busier. The spikes are enormous, and it barely drains between them. Nothing changed except how close to the edge we were. And here's the number to remember. Average weight scales with rho divided by 1 minus rho, where rho is your utilization. At 50%, that factor is 1. At 80%, 4. At 90%, 9. At 95%, 19. At 99%, 99. As utilization approaches 1, the weight approaches infinity, and it does so fast. That's why the last 10% of capacity is not like the first 10% at all. So the practical rules. Don't plan to run above about 80% utilization on anything latency sensitive, and if you're above 90, you're already in the steep part of the curve. Reducing variability helps as much as adding capacity, which is why a single queue feeding several servers beats separate queues, and it's why supermarkets and airports move to that layout. And measure the 99th percentile, not the mean, because the mean of a heavily skewed weight distribution describes almost nobody's actual experience. The honest caveat: real arrivals often aren't Poisson. They have daily peaks, they're bursty in correlated ways, and users retry when things are slow, which creates a feedback loop the basic model has no concept of. Real service times vary too, and that variability makes everything worse than the formula predicts. Treat these numbers as the optimistic case. Reality is generally more painful than the model. One sentence. Queues are caused by variability, not by lack of capacity, which is why a system with spare capacity still has queues and why the last few percent of utilization costs so much. Next episode, a distribution where the average genuinely misleads you. Most people earn less than the average wage, and that isn't a paradox or a statistical trick. It's what happens when a shape is skewed.